should run out, because it is very, very unlikely for us to have the exact right amount of reactants to form products. So we're going to go back to that combustion of propane, which we derived earlier we found the empirical formula, which was C3H8, and that happens to be the correct thing. And if we actually balance that equation, we're going to have C3H8 plus 5O2 leads to 3 carbon dioxides and 4 waters. So if you start with 110 grams of propane and 352 grams of oxygen, we know that one of those is going to run out. And we need to find out which one it is so we can determine what our theoretical yield is. So for both of them, you want to start off by finding the moles of each one. So if we have 110 grams of propane, that's going to be equivalent to 2.5 grams of, or 110 grams of propane is going to be the equivalent to 2.5 moles of propane. And if we do the same thing for oxygen, 352 grams is going to be equal to 11 moles of oxygen. And then once you have the moles of each one, what you want to do is pick one of your products to act as your standard. So in this case, we are choosing carbon dioxide to act as our standard. And if we look at our balanced equation, what is the ratio between propane and carbon dioxide? Yeah, it's 1 to 3. So what we're saying is that for every mole of propane that we use up, we're going to be making 3 carbon dioxides. And that's why under the moles of propane bullet point, I have written 2.5 moles of propane is going to be 7.5 moles of carbon dioxide. All we did is multiplied by 3 because propane and carbon dioxide are in a 1 to 3 ratio, so we multiply by 3. And oxygen, we have to do something a little bit different. So oxygen is in a what ratio with carbon dioxide? Not 5 to 3. Or I would say, how would you write your conversion factor? So if we started with 11 moles of oxygen, what would our conversion factor look like? Right, we're going to have 3 moles of CO2, and we're going to have 5 moles of oxygen on the bottom. And then our units are going to cancel out. We're going to get rid of moles of oxygen on both sides, and we'll be left with 11 times 3 divided by 5, which is going to give us 6.6. So if we look at these numbers, if we use up all the propane that we are given, which is 110 grams, we could make in total 7.5 moles of carbon dioxide. If we use up all of our oxygen, then we could make 6.6 moles of carbon dioxide. So the one that we're making less of, so in this case, we're comparing 7.5 to 6.6. The 6.6 means that we are going to run out of the oxygen before we run out of the propane. So in this case, our limiting reactant is going to be oxygen, because if we compare it to the amount of product that we can make, we make less products with oxygen, because we're only making 6.6 moles instead of the 7.5 moles that we would make if we were using up all of our propane. So that ties directly into yield. So if we want to find the theoretical yield of this equation, what we have to do is figure out what our limiting reactant is, which is what we've already done. We figured out that it's oxygen. And then we want to figure out, in this case, what is the maximum possible amount of carbon dioxide that we can form. So we know that we can form 6.6 moles of carbon dioxide if we use up absolutely all of our oxygen. So if we just multiply that by its mole ratio, by its molar mass, we are going to see that 6.6 moles of carbon dioxide is the same thing as 290.4 grams of carbon dioxide. So if in our actual experiment we only made 248.5 grams of carbon dioxide, then we could figure out our experimental yield. And how would we do that? What's our general equation for finding our experimental yield? Yeah, we would take our actual yield, which in this case would be 248.5, and then we divide it by our theoretical yield, which would be 290. And that is going to give us roughly an 86% overall yield. So normally, your experimental yield will be lower than your theoretical yield. Now, that is not always the case because occasionally you can have certain cases where either there's contamination in your sample. So this is like if you're actually working in like your lab and you figured out that you had like 114% yield or something like that. That means either your sample is contaminated with something else, there is, or there's something like it's not dry. Like let's say you're precipitating a salt and you wanted to measure how much salt you got back. Well, if you don't dry the salt, then you're also going to be measuring whatever water came along with it, and that will inflate your experimental yield. But under normal circumstances, generally, your experimental yield will be lower than 100%. So, 348 for the experimental yield? Huh? What? Yeah, so I'm saying like if you actually did this reaction, and this is what you measured, what was the second part of that? Oh, so generally if you're asked to actually find like the percent experimental yield, you will need to be given whatever you got back in the lab, because otherwise it would be impossible to find your experimental yield. It is, I mean, you could be asked to find the theoretical yield, and you should be able to do that just by, you know, given the information like this is what you're starting with, this is what you're ending with. But if you're not given, like, you know, you made this much or whatever, or you recovered this much product, then it would be almost impossible to figure out what your experimental yield is. Yeah, I mean, like if they gave you like 86% yield, you could figure out how many grams that was because you just multiply that 86% times your theoretical yield, and then that would give you your experimental yield.